Okay, hello, Analysis 1A, here we go. Very quickly, for period 4, this might be a little bit repetitive, but okay, too bad. Here we go. Yeah, so I want to find a rule that will enable me to take the derivative of any so-called power function. And the idea here is like, okay, I want to differentiate x squared, I want to differentiate x cubed, etc. How do I do these things? Well, the derivative of x squared is the limit, as h approaches 0, of x plus h squared minus x squared over h. What's the limit as x approaches, what's the derivative of x cubed? It's the limit as h approaches 0 of x plus h cubed minus x cubed over h. And, okay, like in general, every one of these sorts of so-called power functions exhibits a kind of a certain pattern. And here, maybe just doing these really fast to get us kind of warmed up. Well, what do we get here? This is the limit as h goes to 0 of, well, when you expand this out, you just get x squared plus 2xh plus h squared minus x squared all over h. And that, well, okay, in the interest of space, I guess I'm going to not show all the steps, but of course the x squareds cancel, and then I can divide by h, and so this becomes the limit as h goes to 0 of just 2x plus h, and so the answer is 2x. Okay, so that's a pretty straightforward, simple fact, and actually some deep things to say about that, but not right now. What's the derivative of x cubed? Well, it's x plus h cubed minus x cubed, so okay, similarly, you know, like if I can do limits, then I can do derivatives. How best to deal with this? I did this exact problem last week. Some people suggested difference of cubes, which is perfectly reasonable suggestion, but no, I don't feel like it. I'm just going to expand this out. If I expand this out, how do I do that? Well, there's just kind of a rule for cubing a binomial, and it's something that you learn, you know, in middle school by brute force, or potentially with aid of the binomial theorem. You know, you get this kind of like 1, 1, 1, 2, 1, 1, 3, 3, 1 thing. So what do you get? You get x cubed plus 3x squared h plus 3xh squared plus h cubed. You know, math fact, that just is what you get when you cube this binomial, minus x cubed all over h. And, you know, once again, the x cubes cancel. And in the interest of space, we will just do this all kind of in one step. The x cubes cancel. Every other term in the numerator has an h in it. So if I'm dividing by h, then I get 3x squared. Sorry, this should be an h here. 3x squared h plus 3xh squared plus h cubed. But okay, still, these three remaining terms have h's in them. I divide by h, and I get 3x squared plus 3xh plus h squared. And when I take the limit as h goes to 0, I get, in fact, 3x squared. Okay, so there is a pattern, and without further ado, let's just find that pattern. So what is the derivative of x to the n? Built into this derivation is that n is like a positive integer. So for positive integer n, how do I differentiate power function x to the n? Well, I just do the exact same thing that I have been doing for the last couple of minutes. It's going to be, based on the definition of the derivative, the limit as h goes to 0 of x plus h to the n minus x to the n. And here I'll try to write my h's and n's kind of very different from each other. And, well, there it is. So the strategy is exactly the same, just what makes this problem difficult is just the fact that I'm trying to do it in general for any possible power function. So since I don't know what n is, I have to sort of speak generally about x plus h to the n. And okay, what's been the strategy for the previous two problems? In both cases, I had this kind of x plus h squared, I had this x plus h cubed. What did I do with it? I just expanded the whole thing out. And that's what I need to do now. I need to expand out x plus h to the n. How? Well, there is a formula called the Binomial Theorem, which tells you precisely how to expand a power of a binomial. And so, all you have to do is just, know the binomial theorem. So let's know it. What is x plus h to the n? Well, recall from I don't know, a very long time ago that this is really like a kind of a combinations problem, is a counting problem. I need to, let's just start. I get x to the n is the first term, plus, then the next term is going to have some number of x's, specifically x to the n minus 1 of them, and kind of like 1h. And how many of those terms do I get? Well, the way I taught this at the time was, the number of x to the n minus 1 h to the 1 terms is the number of paths through a choice tree in which you chose h one of your n times. And so there are sort of n choose 1 ways to do that. Okay, and maybe the rest of this is coming back to you now. This is n choose 2, x to the n minus 2, h squared. And, okay, let's throw in a dot, dot, dot. This let's go to the second to last term, which is n choose n minus 1. That means now that of your n choices about whether to pick x or h, you picked h, n minus 1 of those n choices. And finally, the last term is n choose n. So now you've chosen h sort of all of the times you chose h. And technically, the full binomial theorem has this coefficient as n choose 0, because now you're choosing h sort of 0 of the times. Okay, so anyway, all of that, let me put some sort of purple brackets around it or something, is simply the binomial theorem. And now we subtract x to the n, and then the whole thing is over h. Okay, so expanding this out a bit, well, n choose 0 just is 1. So that's I put that in there just to kind of show off or something, but n choose 0 is the number of ways of choosing 0 objects from a set of n objects. There's just one way to do that. So I really do get a cancellation here, exactly as I did above in the two special cases. And so I'm left with a whole bunch of things. Let's just write out all those things. So I get the limit as h approaches 0. What is n choose 1? Well, it's the number of ways of choosing one object from a set of n objects, so that's just n. So I get here n x to the n minus 1 times h plus, what is n choose 2? Okay, well, it's not kind of super maybe important that we know n choose 2, but I'll just tell you what it is. Given n objects, it's the number of ways of choosing 2 of them. And so, in fact, it's just n minus 1 over 2. I hope I'm doing that right. Yeah, I guess that's just right, yeah, because you can even just use the formula. But that also just makes sense because, well, yeah, you have n choices for the first object and n minus 1 choices for the second object, but you need to divide by 2 because you've double counted there. Anyway, never mind. It's going to turn out to not matter. And this is x to the n minus 2 h squared. So throwing in the dot dot dots here. What is n choose n minus 1? Well, it's also in fact n minus 1 over 2, because you're picking. No, sorry. It's take it back. N choose n minus 1 would just be n. Because you're choosing how many ways given n objects of choosing n minus 1 of them. Well, you're effectively choosing all but one, so you have n choices of which one to not pick. x times h to the n minus 1, and finally n choose n is just 1, and so this is h to the n. Okay, so possibly wasting time here a little bit, but these have canceled, and I kind of got rid of some of that combination notation. Well, look, the only term inside the purple brackets that didn't have an h in it was the first one, and that got subtracted out. Every remaining term has an h. And so, finally now, I will divide through by h. And when I divide through by h, what do I get? I get n, x to the n minus 1, plus n minus 1 over 2, x to the n minus 2 times h. I took one h out of this. A bunch of other terms, which are still going to have h's in them. Nx to the nx times h to the n minus 2, because I'm dividing by h, plus h to the n minus 1. Okay, but all of this is sort of doesn't matter, because just like above, you're really going to get this leading term, and then you're going to get a whole bunch of terms which now just die as h goes to 0. And that's exactly what happens here. That goes to 0, that goes to 0, that goes to 0, and all this stuff in there goes to 0 as well. And the answer to this problem is just nx to the n minus 1. Okay, this is amazing, incredible, wonderful, and I love it. Here's what it says. It says that the derivative of x to the n is just nx to the n minus 1. This is amazing because it means that in the future, when faced with some differentiation problem, like, hey, what's the derivative of x to the 5th? Instead of computing this via a limit, I can simply now use this rule which I've proved in general. And what is the derivative of some power function x to the 5th? Well, according to this formula, it's just 5x to the 4th. And that is like basically no work compared to the work that's required to differentiate using the so-called definition, using the limit definition. Okay, and there are a couple things to add. So this happened. This power rule, it didn't happen in period 3, it did happen in period 4, period 6, who knows, that's tomorrow. But there are some other rules that we were developing. What were those rules that we developed? There was a rule 1 that said that the derivative of a constant function was 0. There was a rule 2 that said that the derivative of the sum of two functions was the sum of the derivatives. There was a rule 3, which I barely discussed, but maybe I will now. No, I won't discuss it, I'll just mention it now, that the derivative of a constant times a function is the constant times the derivative. And now there's this kind of rule 4, I guess, if you want to call it that. Okay, well, why am I mentioning these again now? Because really, if you sort of appreciate what's going on, this is kind of a callback to a different conversation we had last week. But look, if I know how to differentiate constants, and I know how to differentiate power functions, and I know how to differentiate constants times functions, and I know how to differentiate the sum of two functions, then what kinds of functions can I now differentiate? Well, I can now differentiate any function which is a sum of a bunch of functions which are constants times power functions. Well, I've in fact just described polynomials. I now have the ability to differentiate any polynomial. And so, maybe I'll sort of do it over here. You know, give me some polynomial, like f of x equals, I don't know, 5x cubed minus 4x squared, you know, plus x minus 3. Okay, well, here we go. I'm going to differentiate this now. How? Well, I apply a rule that says that the derivative of this function is just the sum of the derivatives of the individual pieces. And so that's the derivative of 5x cubed minus the derivative of 4x squared plus the derivative of x minus the derivative of 3, running out of space a little bit. Hopefully that's still legible. Okay, well, what is the derivative of 5x cubed? It's going to be 5 times whatever the derivative of x cubed is. No one writes this out, but I'm doing it just this one time. What is the derivative of 4x squared? Well, it's minus 4 times whatever the derivative of x squared is. What is the derivative of x? Well, it's just the derivative of x. And what's the derivative of 3? Well, we know that the derivative of 3 is 0 by our rule 1. So I applied rule 2 to split this up into 4 different derivatives. I applied rule 3 to say that I can just take constants out. I applied rule 1 to say that the derivative of a constant is just 0. Now I'm going to apply the power rule. What is the derivative of x cubed? Answer, okay, we did that already. It's 3x squared. What is the derivative of x squared? It's 2x. What is the derivative of x? It's just 1. Okay, and so maybe this wasn't that impressive because I actually only used powers that I knew from the top of the board. But the answer is that this is 15x squared minus 8x plus 1. And suddenly, okay, every single person in the whole world actually just does this in about 10 seconds, just going straight. So this work that I just showed here, I will never show again. But I just want to justify what I was doing because we can, in the future, just follow this red arrow and just go immediately from the polynomial to the derivative, kind of by formula. With a combination of the sum rule, the constant rule, the power rule, I now have a method for differentiating polynomials that's great and simple and easy. Okay, last little thing, our textbook, which we are basically, I don't want to say stuck with, because that makes it sound bad, but we are using our textbook, and so since we're using our textbook, we're following the textbook's style and everything like that. And our textbook decides, for whatever reason, to start using an extension of the power rule without proof. So I'll just call it like, extension of power rule. Okay. So it goes like this. Suppose I want to take the derivative of, I don't know, like 1 over x cubed. Well, okay, is that a power function? I guess so. It's a power function, however, with a negative exponent, with a negative integer exponent. So I mentioned, I kind of erased it already, but I did mention it, that our proof only applies to positive integer exponents. Yet, even though, here is the power rule that I'm reminding you of, even though our proof depends on n being a positive integer, the power rule is also true for negative integers. So the book asks you, and I am asking you too, to just trust us for a minute, and we will just use the power rule also for functions like this. And okay, what is the derivative of x to the negative 3? Well, you have to be a little bit careful. What does the rule say? The rule says the derivative of x to the n is nx to the n minus 1. And so the derivative of x to the negative 3 is, bring down that power, negative 3, x to that number minus 1. So x to the negative 4. And so if you want to, you can write this like this. Okay, so this is true, but I haven't proved that this is true. So loose end, which I will take care of like next week or something, or later, the proof that the power rule applies to negative integers as well as positive integers. And there's even more. Suppose I want to take the derivative of of like x to the 5/3. Okay, that is also a power function, I guess. But now the thing I'm differentiating is not even an integer, and it's absolutely true that that my proof from 10 minutes ago is not applicable to situations like this. Nonetheless, this is still true. So our book wants you to take their word for it, and please take my word for it also, that the power rule also applies in these kinds of situations. And so, okay, what is the derivative of x to the 5/3? It is, according to the rule, 5/3 x to the, and you subtract 1 from the exponent, so 5/3 minus 1 is 2/3. And so that's another thing that you're expected to just do. And okay, you can basically do all sorts of combinations of this. You know, I don't know. You can even differentiate x to the negative 2/3, and if you do that, what do you get? Well, again, the rule just works, right? Negative 2/3 x to the. Now you subtract 1 from the exponent. You always go down a power, so it's like negative x to the negative 5/3 even. So okay, so I will just leave it at that. If you want a challenge, you could just try to prove these things to yourself now using the definition of the derivative, or you can just agree to trust me, and we'll handle this in the coming weeks. Okay, that was the power rule. Goodbye.